Now, all we have to do is enable the corresponding checkbox to generate the liquid mesh. And here is the object that was created, which is essentially an envelope around the particles. Deactivate the wireframe visualization as well. The uppers factor allows us to increase the base resolution by a predetermined amount. Something similar happened with smoke. The particle's radius attribute is interesting and could be useful in some situations. To better understand this, let's visualize the particles. As previously stated, the liquid object is created by adding a mesh around the particles. Blender computes the virtual size of the particles to accomplish this. These particles are used to shape the mesh. As a result, increasing this value effectively expands the object. Setting the particle radius to 4, for example, causes the mesh to grow in size. Keep in mind that any changes to these parameters must be made at the start of the timeline. Otherwise, the update is not visible. When this value is set to 1, the mesh adheres to the particles more closely. The particle radius parameter can also be useful when some areas of the simulation are lacking of liquid. It is common for the liquid to have some holes in it. Increasing the particle radius is a simple trick for filling these gaps. However, keep in mind that increasing the radius reduces the liquid details. When this becomes obvious, you must add more particles and details by increasing the global resolution. The properties listed below can be used to smooth the liquid surface. You can see it here. This is how a liquid surface looks in general. You can achieve a more regular surface by adjusting the smoothing and concavity factors. Well, when I increase the uppers factor, this is what happens. This is due to the fact that increasing the mesh's resolution results in more details. It is also more closely shaped to the actual particle distribution. The highly irregular shape is also due to the distance between the particles, which resulted in numerous holes. By increasing the number of particles, we can achieve a more regular shape. This can be accomplished using the resolution division parameter as usual. As you can see, the final outcome is the result of many factors interacting with one another. And changing the global resolution has an effect on the appearance of other parameters. Finally, think about the distance at which the simulation will be visible. When you see it from a distance, you don't need much detail or resolution. This can save you a significant amount of computation time. We have to take into account another important property, the use speed vectors one. Consider the fact that the motion blur feature is not used in the case of fluids. This means that enabling motion blur has no effect on fast-moving liquids. In this case, the use speed vectors can be useful. It basically computes and stores each particle's movement. Then, in post-production, we can use this information to generate a simulated motion blur. As a result, I recommend that you always enable this option. Otherwise, if we compute the entire simulation while this property is disabled, we will have to compute it all again. Then there are the additional components, such as spray and foam. But we'll think about them later. And now, as usual, we must consider the cache. It is critical because it allows us to save and store the simulation to disk. We've already covered the fundamentals of the cache in the case of smoke and fire. First, we must select the frame range to bake. Then we have some cache type options. The replay method is the default, and what we previously used. This means that the simulation is run while the timeline is being played. All instructs Blender to bake all of the simulation's components before playing the timeline. Finally, using modular, as we saw with smoke and fire, we can bake the three components separately. First, we'll bake the basic fluid simulation, which essentially represents the movement of all liquid particles. We can bake the mesh once we have this. Finally, we can bake the remaining particles, such as spray and foam. And I strongly advise using the modular method. This allows us to fine-tune only one component at a time. We can, for example, compute the liquid, and then only adjust and recompute the mesh component. When we're happy with it, we can adjust the other particles, bubbles, and spray. Finally, don't forget to enable the resumable option. This allows for significant time savings. We can compute a few frames and immediately evaluate the simulation's quality. If everything is fine, we can begin baking. Consider naming the folder where you want the cache to be saved. Otherwise, Blender will generate a random name, which can be confusing when we have a large number of simulations. Only one more thought about the liquid source. We can also enable the initial velocity property. When we have a moving liquid source, this is useful. As a result, the liquid flows in the same direction as the source. But we don't need it in our case, as we don't have a moving liquid source. Now we must specify the frame range in which we want the simulation to begin. Essentially, some frames before the impact. This prevents Blender from calculating unnecessary frames. As a result, we must simulate the impact of this object on the water. To do so, we must assign this piece the effector behavior. Additionally, collision must be the effector type property. We can see the impact here, as well as how the object causes some waves in the liquid. However, water escapes from the container as well. This is due to the fact that the fluid is now moving very quickly, which, as previously stated, can cause collisions to be missed. When we disable the collision object, the water is properly confined within the pool. Let us try to solve this problem. As you may know, an approach involved increasing the resolution of the simulation. Blender now has more details to work with, allowing it to detect liquid collisions caused by fast-moving objects. Furthermore, we could increase the timesteps values. This could be useful for extremely fast-moving objects, or when the resolution cannot be increased significantly. The collision, however, is not very energetic. There is no splash in the water. The issue is that we don't have any property to increase the energy of the impact with this collision object. The impact is calculated using the object's mass and velocity. As a result, the only way to increase the force of the impact is to increase the velocity of the falling object. But that is not what we intend to do. We have two options for accomplishing this. We could, for example, duplicate this object and make it bigger and faster. And we could use this object only for simulation, rendering it invisible. However, we have a better solution. And it consists in setting the object as guide. This property was briefly demonstrated in smoke simulation. It is used to add velocity to the liquid or smoke as a result of the collision object. Essentially, the collision object's velocity is transferred to the liquid. As a result, when the object comes into contact with the water, its velocity is transferred to the liquid particles, causing them to move in the same direction as the collision object. The distinction is that, when the object is set to collision, Blender computes the actual physical collision, and the particles move as a result. On the other hand, with the velocity factor, we can precisely define the velocity that must be transferred. By adjusting this parameter, we can define the energy of the impact. Let's take a look at the simulation. Nothing appears to happen. This is because, in order to activate the guide object, we must enable the related property in the domain. This enables another algorithm, which unfortunately requires more computation time. In the velocity source parameter, you must also select the effector option. Otherwise, another domain would be used as the velocity source. You can also see how slow the computation has become. As a result, I'm going to reduce the global resolution. But, once again, nothing appears to happen. This is due to the fact that we must increase the velocity factor parameter. And now we can see the result. I also want to mention that I set the cache type to all. When using guides or running complex simulations, the replay cache type can cause problems. You must manually bake the simulation when using the all cache type. The simulation is saved to disk by Blender and is not played in real time. When you change some parameters, you must release the actual bake and start over. Well, let's boost the velocity factor even more. We can clearly see how increasing this factor increases the impact's energy. We can also increase the impact's power by adjusting the same velocity factor in the domain. This is a global multiplier factor that applies to all guide objects in the simulation. So, if we have a lot of collision objects in the simulation, we can change the global energy of all of them by changing this value. If I raise this value, the collision becomes even more powerful. We can also see single particles moving very quickly upwards. If you notice a large number of particles moving in a chaotic manner, you can use the apic method or decrease the flip ratio parameter, as previously discussed. We can now create the mesh and start over with the baking. Here is the end result. The fluid is clearly blobby, as we can see. This is due to the low resolution. And this is the final, much higher resolution result. The division of resolution was set to 256. This is not the ideal resolution, it should be around 512. However, remember that with such a resolution, the computation time can be quite long. But for the time being, it can be enough. Here's an example of the other method I mentioned earlier, for creating a more energetic simulation. And it is based on making a duplicate of the object. This is used to render, while the other is only used to make contact with the water. We can then change its size and velocity as needed. I also increased the mesh's uppers factor slightly. As a final step, I'd like to make a point about baking. We learned in the previous lesson that the modular method is the best for baking. Consider that, because we have now enabled the guide option in the domain, the first thing you must do is bake the guides. So, first and foremost, I'm going to bake the guide. In this case, it's fast enough. The liquid component must then be baked. Finally, the mesh. We must now proceed with the generation of the extra particles. They are not the liquid particles themselves, but the spray, foam, and bubbles produced when a fast-moving fluid collides with another object, as in this case. They help to make the simulation more realistic. We will not consider all of these factors. They are used to determine the final particle number and distribution. So, all we have to do is choose which particles to generate. However, keep in mind that the number of particles created is also related to the global resolution. As a result, the higher the resolution, the more particles. And there could be hundreds of thousands of particles. And this can significantly increase the calculations. I discovered that the bubbles are the ones that generally cause the most calculations. They can also be ignored, unless you have a close-up shot, or are directly inside the water. Well, as an example, I'll turn them all on. For each of them, Blender will generate a particle system. Remember, as previously stated, to enable the Use Speed Vector property, so that we can add motion blur to the particles in post-production. As previously stated, these parameters are used to estimate the number of particles. However, we do not define this number by simply typing a value. They essentially define the propensity that each particle will be generated. And each of these parameters is associated with a probability. So, if we have too many particles, we could change these parameters and try to reduce the total number of particles. And, with modular baking, we can bake only this particles component. So, I'm going to raise the resolution to 64 and begin baking. I also turned off the bubble generation. There is also a strong energetic effect. As a result, I'm going to reduce the velocity factor of the collision object. In fact, the wave is cut at the top of the domain. Back to our particles, they are essentially a particle system, as shown here. The liquid particles are also available in the Particle System tab. They are the particles we saw at the start, the ones that create the liquid. Then there are the spray and foam particles that we just created. We can also see the total number of particles here. They are quite numerous. The color of the particles corresponds to their speed. The color red is associated with the particles that move the fastest. Finally, we must assign a real object to each particle. Their rendering mode is currently set to halo, which means that nothing is rendered. As a result, we must create this object, as well as the associated material. This is the file I used for the final rendering. we have a higher resolution and a greater number of spray particles. And here's the rendering, complete with foam and spray. The simulation resolution is still not optimal, there is still a blobby mesh. However, as an exercise, it can suffice. With such a large number of particles, performance degrades quickly, and navigation becomes difficult. It is preferable to hide the particles in the viewport in this case. You can do so by selecting the domain, then opening the Particle System tab, and disabling the viewport display option. You can also reduce the number of particles displayed in the viewport. I've already cut it in half. If you want to improve performance, you can turn off the simulation's viewport visualization entirely. You must also set the domain display to wireframe. We must now create the spray and foam particle objects. They're just spheres. I also made 2 collections, each with 3 spheres. Given that there will be millions of particles, it is critical to keep the number of faces as low as possible. I made 2 collections of 3 objects, to avoid a problem that we may encounter in some cases. And it consists of a regular particle distribution that appears to follow a pattern. So I'll duplicate the sphere and keep it in its original location. Then, in edit mode, move it to a different location, so that it has the same origin as the original. Now, go to the domain's particle systems, and, in the render section, select collection as the render type. Of course, choose the collection you just made. And, as a result of the previously duplicated objects, the particle distribution will be more uneven. You can also tweak the scale randomness setting. Finally, you must perform some test rendering in order to fine-tune the size of these particles. The materials are extremely simple to assemble. The water is basically made of the same material that we saw in the other pools. In terms of spray particles, it is simply a glass shader with an index of refraction of 1.33. I'm going to combine the glass shader with a diffuse shader to create the foam particles. In this way, we can make the foam whiter. And with that, we finished the section on fluid simulation. Let's take a look at the rendering settings I used. Of course, I chose Cycle as the rendering engine. If you have a CUDA-enabled graphic card, you can enable the GPU compute option. I'm also going to enable the denoise function. As a result, we can drastically reduce the max samples parameter. If you have an NVIDIA card, enable the optics option. It's also a good idea to leave the noise threshold property at its default setting. I used a cinematographic aspect ratio for the aspect ratio. In other words, 2560 by 1080 pixels. I also enable the motion blur setting. However, as previously stated, remember to deactivate it when rendering the water simulation. We will, in fact, simulate it in post-production. We've already discussed the properties of light paths in relation to smoke and fire. It is critical to specify the file format as an image sequence. Never save your scene as a video file. I also recommend the OpenExer file format. Because it is a 32-bit file format, it contains all of the data required for the best compositing and post-production. However, choose a lossy compression method for this, as otherwise each single frame could be very large. Let's take a look at the liquid rendering right now. Let's render at least one frame, so we have something to work with. Then switch to the compositing view. This is the basic node configuration I used. Simply connect a vector blur node as shown here. This is where the vector component comes in handy. Remember that in the liquid mesh properties, we enabled the Use Speed Vector option. This vector blur node can now blur the particle's motion. It's hard to see in the particles, but it's there. This motion blur is applied to the other objects as well. With that, we came to the end of the course, where we learned how to create many of the Blender simulations. So I invite you to try it yourself, making your own setting and using all of the techniques we've seen so far.